This very circuit board will allow us to see that electronics are built on a few simple ideas. Those simple ideas unite all of these complicated looking parts together, making all of this understandable. Take a look at these marbles. When we squish them together, they push harder on each other, and when let go, they move apart. Those marbles are like electrons, and moving electrons are electricity. How strong they push on each other is voltage. It's like an electrical pressure. More voltage means more push. In fact, this is how a 9-volt battery, let's say, can push out electrons to power something. We basically just cram a bunch of electrons on one side, building the pressure. Then we connect the sides and boom, moving electrons, aka electricity. How many electrons flow past a certain point at a time is current, similar to current for water. And just as how water flows from a higher pressure to a lower, electrons do the same. There's one more important piece to the puzzle, and that's resistance. It resists the flow of electric current, similar to how a narrow pipe makes it harder for water to flow. Another thing resistance does is it lowers the energy, the voltage, of the electrons that pass through it. These qualities of voltage, current, and even resistance are useful for electronics. And that's the essence of electricity. Not too bad, hopefully. In the end, electronics basically come down to measuring voltage and creating it. And once you see this, even making your own PCB with PCBWay looks easy, but more on that later because we're getting ahead of ourselves. Let's take a look at our first component. This is a photoresistor, and it seems like it can sense how much light there is. The key to that comes from the material that is used, which is called a semiconductor. When light hits the material, it gives energy to the electrons around the atoms of that material. The electrons can now move around easily, and that would mean a lower resistance because of the ease of movement. When connected with a resistor, a component where its resistance doesn't change, something useful happens at this point when electrons flow through both the resistor and photoresistor. When there's a lot of light, the photoresistor has small resistance, which means that it doesn't lower the voltage of the electrons passing through it very much. When there isn't a lot of light, the photoresistor has a lot of resistance, lowering the voltage much more. We can measure the voltage by connecting this to a microcontroller and taking a reading, sort of like how we use a pressure gauge to measure pressure. Believe it or not, this example shows the entire gist of electronics. Something happens in the environment, a component called a sensor, for example a photoresistor, causes a voltage to change, which can be measured or taken as an input to another electronic component. So let's take a look at this sensor over here, which looks like there's a lot more going on. But believe it or not, it's a similar concept using voltage. Okay, first, a thought experiment. Say you are flicking a marble and it bounces back from a wall. If the wall was further away, it would take a lot longer for the marble to come back to you, assuming you flick the marble in the exact same way. If you timed how long it took for the marble to come back and somehow knew the speed, you can reverse engineer a distance with some math. Well, that's what this sensor does. Except instead of marbles, it's an ultrasonic wave. So introducing the ultrasonic distance sensor. Pretty cool. The question now is, how does the microcontroller get information from this sensor? Well, just like with the photoresistor, it measures a voltage. But this time, it's a little bit different. This ultrasonic sensor creates a voltage pulse, meaning it turns on at some point and then it turns off at another. The time in between turning on and off happens to be the round trip time of the ultrasonic wave. So we just connect the metal pin of this sensor that has the voltage pulse to the microcontroller and then crunch the numbers to calculate a distance based on the time in between the on and the off. And just like that, we gave the circuit board the ability to judge a distance. There are other metal pins to the sensor. 2 of them are for power, which means that you just connect 5 volts to one of the pins and 0 volts to the other. And then the last pin is used by the microcontroller to tell the sensor to start a distance measurement. The microcontroller does this with a voltage pulse, similar to what the ultrasonic does to encode the travel time of the ultrasonic wave. So far, we've seen how voltage is used by the photoresistor, which changes the voltage value to encode how much light there is, and the ultrasonic sensor, which uses a timed pulse to encode the round trip time of the ultrasonic wave. And then there's this thing, a sort of final boss in terms of how it encodes sensor information. As you've seen before, the circuit board can know how much it's tilted, and it's thanks to this guy. It's called an inertial measurement unit, IMU for short, aka EMU. There's actually multiple sensors in this chip. The fast and simple is that there's 3 sensors to detect acceleration in 3 dimensions, 3 sensors to detect how fast we are spinning on each axis, as well as a temperature sensor. And we can use this data to calculate how much we tilt, but now we have 7 different pieces of sensor data, and it all has to go through one wire. The previous 2 sensors only had 1 piece of data to send, so it works out, but now we have 7, so how will we pull this off? Well, let's do a thought experiment, because as you could probably tell, I really love thought experiments. The English alphabet has 26 letters, and we can put those letters together in different orders to create words and meaning. But what if the English alphabet only had 2 letters? A little bit ridiculous, but we can still make any combination of those 2 letters to make words and meaning, as long as we can use as many of those 2 letters as we want. Well, this is exactly what binary is, except the 2 letters are 2 numbers, which are either 1 or 0. We can make different combinations of 1s and 0s and call them different characters, like the lowercase a. Or we can use 1s and 0s in a number system similar to the base 10 system, where each number you write is multiplied by a certain power of 10 to account for the place it is in, and then they're combined at the end to create a number value. In binary, it's similar, but in base 2, because there's only 2 numbers that we can use, 0 and 1 instead of 0 through 9. So now we can use binary to let the microcontroller know which sensor data we are sending, and what the sensor value is. That's how we'll cram 7 different pieces of sensor data through one wire. So we can write number values and characters in binary, but we need to take the binary on paper and put it into metal, so that the sensor can send data to the microcontroller. And once again, voltage comes in to save the day. Here's the thing, voltage levels by themselves aren't too interesting, but combine that with the specific timing of voltage levels, similar to the ultrasonic sensor, and its pulses, we can put the binary in metal, so to speak. Because we only need to represent a 1 or a 0, we can make a high voltage level 1 and a low level 0. This chip sends out patterns of those high or low voltages, one after the other, but how fast should it do it? The microcontroller can use another wire to send regularly timed voltage pulses, and when the pulse is high, that's when a 1 or a 0 can be sent. It's like a conductor waving their hands to help the musicians keep track of the tempo. Being able to get all this information from the 3 sensors is great, but it's not worth much if we can't do anything with it. So let's do something fun and make this LED change based on the inputs of the sensors. We've seen how voltage is useful for sensors, and the same can be said about controlling an LED. Voltage is what allows electrons to flow through the LED and resistor, which is used to limit current, preventing the LED from exploding or burning out. More voltage means more current in a brighter LED. The question is, how do we change this voltage if we can only output a single high value, like 5 volts? Take a look at this LED. It's fully on for most of the time and turns off for a little bit and then repeats that pattern. If we make this pattern repeat faster, then it kind of blends together, making the LED look like it's not blinking at all. It also looks a little bit dimmer than if it was fully on. Now look at this. The LED is off for most of the time, and if we make this pattern repeat faster, then it looks like a much dimmer LED without it blinking. So it just comes down to controlling how long we turn the voltage on and off in a repeated and fast enough pattern. This is called pulse width modulation, PWM. We can take this one step further to control a motor and its speed with PWM. Same concept, just a different output. But this does require a MOSFET, which is a type of transistor. The quick and dirty explanation is that whenever voltage is applied to the gate, it lowers the resistance of the MOSFET, allowing current to flow through a motor, for example. In other words, it's basically a voltage-controlled switch. This allows the microcontroller to control something that requires much more power, like a motor, than the microcontroller can provide on its own. Before we get to the microcontroller itself, I need to mention the 2 parts of this circuit board that support it. Up here is the voltage regulator circuit. It takes a higher voltage, like from a power supply, and then converts it down to 5 volts. That is the required amount that the microcontroller needs. Too much and it damages it. Too little and it won't work at the speed that it needs to. The thing that determines how fast the microcontroller works is this, a ceramic resonator. Apply some voltage to it and it creates a swinging voltage, basically a voltage that goes up and down. The microcontroller has a circuit to sustain the swinging, and it uses it to keep track of time, similar to how the microcontroller creates a swinging voltage for the IMU sensor. And now we've come to the final piece of the puzzle. It's veiled in mystery, sealed off with epoxy, yet is the most important part of this printed circuit board. It has the ability to think, so to speak, which sounds very complicated, but it can be broken into many simple pieces. Remember those things called MOSFETs, which are a type of transistor? Well, you may have heard about how all computers rely on transistors to do what they do, which is to compute things. In other words, to think. And it's true. Turns out, if you arrange transistors in a clever way, you can make logic. Some arrangements only turn on the output when both inputs are on, while other arrangements turn on when either input is on. All these are using voltage, just like everything else we've seen in electronics. We can group these transistors to make digital logic components, and use those to make things that can do math on or remember binary numbers, which are again all represented by voltage levels. Everything is processed at precise times thanks to the timing created by the ceramic resonator. And that's all a computer is, including this microcontroller. A bunch of transistors working together to process an input and create an output. And that's electronics in a nutshell, built on simple ideas that can be put together. Also, everything comes back to voltage.
And we're pretty much done, right? Pretty much everything on this board. Well, electronics may still seem like magic to you because you might be asking yourself, there has to be some sorcery behind actually making one of these. Well, let me take you through a quick tour of electronics design.
Okay, first you start drawing and placing the components you'd like to use. I use KiCad, which is a software for printed circuit board design. We want the software to know how these components are connected, so we just draw the connections. It could be lines or it could be labels. It all means the same thing. And now for the fun part. This is the physical layout where we draw the actual copper wires that would need to be embedded into the printed circuit board. It's pretty much just playing connect the dots, and it's very therapeutic. We can also arrange where each component would physically sit on the board. And check this 3D model out. I mean, it looks pretty close to the real deal, and it also looks very awesome.
Okay, now we're gonna need to get the parts in our hands.
First, I need to send the PCB design to PCBWay, and I do that with this button. The default options and the stencil options are good, so I ordered the PCB. I buy the parts that go on the PCB with DigiKey, and boom, we've got the parts. Now we assemble by soldering. Soldering is essentially melting metal so that we can physically and electrically connect the parts to the printed circuit board and to each other. Now we have a piece of electronics that we can program so that it does something. Through these connections, I can download the instructions, or the program in other words, onto the microcontroller. And after that, we have a final product.
So hopefully I made electronics seem a little bit less magical to you. You're welcome. Or sorry, I guess it depends. But everything said and done, electronics, no matter how much you try and explain it, they still seem like magical pieces of metal that just work. Really goes to show what we can do with our imagination.